All right, let's jump right into this explainer. Today, we're looking at a brilliant piece of engineering known as the Buchholz Relay. In a world that's absolutely packed with complex digital sensors and software, this device really stands out. Why? Because it relies on pure, undeniable physics to keep our most critical electrical infrastructure safe. We're talking about preventing catastrophic explosions in massive oil-filled power transformers.
So what you're looking at here is the exterior housing of the relay itself. It's physically bolted right into the pipeway between a transformer's main tank and its oil conservator, which is basically just a giant expansion tank for the fluid. It's literally sitting right there in the flow of the insulating fluid, acting as this relentless, silent sentry that monitors the health of the transformer 24/7. To put it simply, this relay is essentially a mechanical first responder. It doesn't rely on fancy microchips to do its primary job. Instead, it uses the physical principles of buoyancy and fluid dynamics. Believe it or not, the underlying physics are surprisingly similar to the float in your toilet tank, except, scaled up to protect multi-million-dollar electrical grids from three major fault conditions: dangerous gas accumulation, a severe loss of insulating fluid, and excessively high fluid flow speeds. Here's our roadmap for today. We'll start with the anatomy of the relay, then look at how it detects gas accumulation, reacts to fluid loss, stops high flow speeds, and finally, how it actually sounds the alarm. Section 1. Anatomy of the relay. Inside the mechanism. Let's peek inside the chamber. Floating in that insulating fluid, you'll find three totally vital mechanical parts. Notice the upper float gauge pair near the very top. Directly beneath that is the lower float gauge pair, and right there, hanging in the main fluid pathway, is the flap valve. Here is the absolute crucial point. These internal components, the floats and the flap, they physically move in response to changes in the fluid. And when they move, they do something incredibly important. They activate connected reed-type switches. These are basically simple magnetic switches. They bridge the gap between mechanical movement and electrical communication, sending a signal straight to the electrical controller and monitoring circuit of the transformer. Moving on to Section 2, detecting gas accumulation, the slow buildup. So picture this. Inside an oil-filled transformer, if you get an electrical fault, it can actually cause the insulating oil to break down and literally form explosive gases. Now, because gas is lighter than oil, it naturally migrates upwards. And because of exactly where our relay is positioned in the piping, all that gas collects right inside the top chamber of this device. And as that gas collects at the very top of the chamber, it physically pushes the insulating fluid out of the way. It forces the fluid level down, basically creating this dangerous pocket of gas right at the roof of the device. It is just a perfect cause and effect chain reaction. The gas pushes the oil down, right? And because the oil level drops, that upper float just loses its buoyancy and drops down with gravity. That simple dropping motion instantly triggers a reed-type switch, closing the contact and firing off a warning signal. The physics here, they simply cannot be bypassed. Section 3. Reacting to fluid loss, the critical drop. Now, a massive drop in insulating fluid is, it's incredibly dangerous. Without it, the whole transformer can rapidly overheat and fail catastrophically. The relay is uniquely designed to detect this kind of total, worst-case evacuation of fluid from the pipeway. If the fluid line completely plummets, the oil has drained out so much that both the upper and lower float mechanisms are just left hanging there, totally exposed in an empty chamber. The escalation here is totally sequential. First, as the fluid drops, the upper float goes down. That's your initial warning. But if the leak is severe and the fluid keeps dropping, that lower float gauge inevitably falls too. And when that lower float drops, it activates a secondary, much more critical reed switch. This is a cutoff contact, and its job is to immediately trip the system. Section 4. Stopping high flow speeds, the pressure surge. What happens if a major internal short circuit or fault hits? It can create this massive, explosive pressure wave. This wave literally forces the insulating oil to rush toward the conservator tank at crazy high speeds way over the standard safe limit of 100 cubic centimeters per second. When that happens, that sudden, violent rush of fluid physically slams right into that small, flap valve suspended in the middle of the pathway. The immense force of the surge pushes the flap violently in the direction of the flow. The logic here is just brilliantly simple and incredibly robust. If the flow speed is too violent, the sheer kinetic energy of the oil forces that flap open. Bam! Just like the lower float, when this flap swings, it activates a cutoff reed switch, immediately sending a trip signal to shut the transformer down before it literally destroys itself.
Which brings us to Section 5, sounding the alarm. Alarm versus trip. So there are two completely distinct escalation protocols here. A slow gas buildup that drops the upper float, that triggers a simple alarm. It's kind of like a heads up something is wrong signal. But if you have severe fluid loss dropping the lower float, or a massive pressure surge swinging that flap valve, the relay triggers an immediate, mandatory trip. This is a hard cutoff signal that steps in to shut the entire transformer down. And the operational response for these two states is totally different. An alarm means operators need to actually walk up to the device, look through the inspection window, and use a built-in extraction valve to safely pull out that accumulated gas so they can analyze what's causing the fault. But a trip state, that means the relay just physically intervened to save the grid from an imminent explosion. The power is cut, and operators have to thoroughly investigate. Interestingly, if that flap valve is triggered by a massive surge, it actually locks itself into place. An operator has to manually release it using a built-in test button once everything is finally safe to turn back on.
It is honestly just fascinating that in our highly digital world, where literally everything is run by complex software and microprocessors, the ultimate line of defense for our most critical electrical infrastructure still relies on the pure, undeniable physics of a simple float in a pool of oil. Next time you drive past a massive electrical substation, ask yourself, isn't there something incredibly reassuring about a safety mechanism that absolutely cannot be hacked, just because it relies entirely on gravity and flow? Thanks for joining me on this explainer, and keep questioning how the world around you actually works.